some equations are more difficult than others to balance by inspection. And here's one. And I want to show you another technique you can use with any equation in order to try and balance. So here's my equation Al4C3, which is solid, added to liquid water, forming solid aluminum hydroxide and CH4 gas. CH4 is methane or natural gas. And so what I do is I set my initial conditions and I divide my sides up into a reactant side and a product side, and I simply list how much of each element that I have. So on the reactant side, I have 4 aluminums, I have 3 carbons, 2 hydrogens, and 1 oxygen. On my product side, I have 1 aluminum, 1 carbon, 7 hydrogen, and 3 oxygens. And again, this is just a way of keeping track when I'm balancing of how things are going. Well, in keeping with my general pattern of balancing metals first, I'm going to balance the aluminum. So my reactant side I have 4. I need to get 4 on my product side, and I can do that by placing a 4 in front of the AlOH3, which is the aluminum hydroxide. When I balance the aluminum by putting a 4 in front of the aluminum hydroxide, I cause what I'm going to call a cascade change, because that 4 not only represents that 4 times the 1 aluminum to make it 4 aluminums, but it then has to be multiplied by the subscript outside of the parentheses for the polyatomic ion, and it then means that I have 12 oxygens, okay? And it also means that I have 12 hydrogens represented in the aluminum hydroxide. Now the 12 hydrogens in the aluminum hydroxide have to be added to the 4 hydrogens in the methane, the CH4, so it gives me a total of 16 hydrogens. So just by placing that 4 in front of the aluminum hydroxide, I have changed the number of hydrogens and oxygens on the product side as well, and I'm going to have to go back and make sure that those balance before the equation can be declared balanced overall. Now, even though I've changed the number of hydrogens and oxygens on the product side, I still use my basic rules, which say I have to, at least for me, and I think it works for most people well this way, I want to balance my hydrogen and oxygen last. So I'm going to go ahead and balance my carbons before I attack the hydrogens and oxygens. I know that I have 3 carbons on the reactant side. I have just 1 in the CH4 on the product side, so I'm going to put a 3 in front of the methane, the CH4, in order to balance the carbons. Now, this also is going to affect the number of hydrogens I have, but I will deal with that when I come to it. So here's what the cascade effect looks like as a result of changing the number of carbons. I now, instead of having 16 hydrogens on the right side, I've increased that to 24 because I have 12 hydrogens in the aluminum hydroxide, and I now have 12 hydrogens in the CH4 or the methane because of the 3 coefficient there. So that I have to look at, because next I'm going to balance my hydrogens. I balance both my metal, the aluminum, my non-metal, the carbon, so I'm ready to go after hydrogen, and that's what's coming. So I'm going to go ahead and balance my hydrogens next. I know that I have 24 hydrogens on the right-hand side coming into this, and I have just the 2 hydrogens in the H2O on the left. I need to get to 24, and the way that I'll do that is by putting a coefficient of 12 in front of the H2O. The 12 times the subscript 2 on the hydrogen would give me 24 hydrogens, and I have now balanced the hydrogens. Now, in balancing the hydrogens, I am going to change the number of oxygens as well, and I'll deal with that next. So at last I have balanced my aluminums, I've balanced the carbons, I've balanced the hydrogens. I just have to balance my oxygens. And as I look at this, I look on my product side. I have 4 times 3 is 12 oxygens on the product side contained in the aluminum hydroxide. Remember that that subscript of 3 outside the parentheses representing the hydroxide ion, OH, is multiplied by the subscript following the oxygen, which isn't shown because it's a 1. So there are 3 oxygens represented there. With the 4 coefficient, you multiply that times the 4, which shows 12 oxygens altogether. When we go to the reactant side, we have 12 H2Os, meaning that there are 24 hydrogens in that water, there are 12 oxygens. So by balancing the hydrogens, we serendipitously balance the oxygens as well. I have 12 on each side, and my oxygens are balanced. So let's do a final check. We have Al4C3. There's 4 aluminums in that. There are 3 carbons. When I go to the product side, there's a 4 aluminums in the aluminum hydroxide, and there are 3 carbons in the methane, the CH4. I look at my water. I have 12 times 2 is 24 hydrogens in my water. I have 12 hydrogens in my aluminum hydroxide, and I have 12 hydrogens in my methane, my CH4, so that is balanced. I have 12 oxygens in my water. I go to my product side, and I have 12 oxygens in my aluminum hydroxide. So my reactant side, my product side have the same number of each atom. They are rearranged in this reaction, but nothing is created, nothing is destroyed. A simple rearrangement, and this equation is balanced. We have done balancing equations, which is very important. But now we want to take the chemical equations that represent reactions that occur and talk about the major types. And the major types that we're going to deal with here are single displacement, double displacement, and double displacement reactions have 2 what I call subtypes, 2 very special types. One is precipitation reactions, the other are neutralization reactions, and we'll talk about those more later on. Then we have synthesis reactions, decomposition reactions, and combustion reactions. So the major types of chemical reactions that we're going to focus on early in this course. First type of reaction that we're going to deal with is called a single displacement reaction, and this is the general form. For metals, the general form is A plus BC yields AC plus B. A and B are metals, and these generally occur in aqueous solutions. The elemental form of the metal is in a solid phase. The ionic compound is in an aqueous phase. And one thing I do want to say about this, all single displacement reactions are also known as oxidation reduction reactions because electrons are transferred in these reactions. So please be aware of that we can not only name these as single displacement reactions, but we can name them as redox or oxidation reduction reactions. Now, there also are single displacement reactions in which halogens replace other halogens that are in solution, and the halogens are nonmetals. They're group 7A or 17 elements: fluorine, chlorine, bromine, and iodine. And you can see here A plus BC yields BA plus C. A and C are halogens, and those also can take place, and those also are oxidation reduction reactions. Here are some examples of single displacement reactions involving a more active metal displacing a less active metal in solution. Our first one is calcium. Solid calcium added to aqueous iron 3 chloride will yield calcium chloride and iron metal. The second is solid aluminum added to aqueous copper 2 chloride will form aluminum chloride, aqueous aluminum chloride, and copper metal. And then finally, here we have an example of a very active metal, sodium, being added to water, liquid water, and the sodium will displace the hydrogen from the water and form sodium hydroxide and hydrogen gas. Now, what I'd like you to do is pause the podcast at this point and go ahead and balance these equations. All the practice that you can get balancing is very important. And then when you're done balancing these equations, resume the podcast and we'll look at the answers. Here are the results of the balancing. 3Ca plus 2 FeCl3 will yield 3 CaCl2 and 2 Fe. 2Al plus 3 CuCl2 will yield 2AlCl3 plus 3Cu. And then finally, 2Na plus 2H2O will yield 2NaOH plus H2. Now, in a future podcast where we deal with predicting chemical reactions, we will look at what's called an activity series of the metals, and you'll see why calcium can replace iron, whereas if you had iron metal added to calcium chloride, no reaction would occur, and we'll be able to predict those using the activity series. That'll be coming up in a future podcast. Here we have single displacement reactions using halogens, and one of the things that you're going to notice is that the free elemental halogen, whether it's fluorine, chlorine, or bromine, or iodine, these will always be diatomic in their elemental form. So we have F2, Cl2, Br2, and I2. Now, the reactions that I've written here are not under standard conditions, meaning they're not at room temperature, and that's one of the reasons that all of these are going to be gaseous in terms of the free element. Generally, under room temperature conditions, bromine would be a liquid, and iodine you could see probably in more solid form. But here we go. We have fluorine replacing the chlorine and sodium chloride to form sodium fluoride and chlorine. In the next reaction, we have chlorine gas replacing bromine in calcium bromide and forming calcium chloride and bromine. And finally, we have bromine replacing the iodine in aluminum iodide to form aluminum bromide and iodine. If you would, go ahead and pause the podcast so that you can balance these, and we'll look at the results next. So let's look at the results of the balancing here. We have F2 plus 2NaCl will yield 2NaF and Cl2. The second one is balanced as written. All the coefficients there are 1. And then the third one, we have 3Br2 plus 2AlI3 will yield 2AlBr3 plus 3I2. How'd you do? This is the end of part 2 of the video podcast series having to do with balancing chemical equations and reaction types here at Ontario High School. I want to leave you with another quote from Ayn Rand. And I want to give you this caveat. Because I put these quotes at the end does not necessarily mean I endorse what they say, but I think they're worth reading and worth hearing to provoke thought, and you should be thinking. So, here we go. Government help to business is just as disastrous as government persecution. The only way a government can be of service to national prosperity is by keeping its hands off. Something to think about. So, I wish you well. Stay tuned for part 3.